Soft spheres and Yukawa potentials. Two different problems, one powerful tool, the Born approximation. And here's where we start to actually see the Born approximation come into the general landscape of physics. We start with the wave equation, which is given from, in this case, Schrödinger's equation. We find a Green's function that allows us to put this Schrödinger equation into the integral form that we had discussed, from which we approximate using a Born series. That Born series gets truncated, and that leads us to the first order Born approximation, which we get to the kinetic or the kinematical scattering. This picture is a great summary of what's going on here, and this is from this group here they made this in conjunction with the electron microscopy. So this is really darn cool to see a pictorial representation of the flow of things. Okay, so enough rambling about the background. What is going on with these problems? Well, today we have a 2-for-1, problem 10 and problem 11. Problem 10 wants us to find the scattering amplitude, which is what the Born approximation allows us to do, for a soft sphere scattering at arbitrary energy. Show that your formula reduces to equation 10.82 in a low energy limit. We love this limit, don't we? Then we want to evaluate the integral in equation 10.91, which by the way is making reference to an example dealing with the Yukawa potential, to confirm the expression of the final scattering amplitude. Okay, so this whole thing comes based on the Born approximation, and that's a method in quantum mechanics used to calculate the scattering amplitudes when particles interact with the potential. It's a perturbative approach, assuming that the interaction is A, weak, and B, the incident wave is only slightly altered by the potential. Okay, so remember a couple questions ago how we had that leading term that we got rid of for the hydrogen ground state? That's what that means. And this approximation simplifies complex scattering problems, making it crucial for studying various physical systems, such as the atomic, nuclear, and particle interactions, where the exact solutions are, just difficult or impossible to obtain. Okay, and that's what we saw with that flow chart with the microscopy going on. But the reason why we care ultimately is that its importance lies in providing a practical first order approximation that helps predict experimental outcomes. This is really what we're all about right now. Okay, these are all in the applications of quantum mechanics. So the challenge for you is knowing that we're dealing with the Yukawa potential in problem 11, what is the importance or what is important about the Yukawa potential? Where is it used? How is it used? You've probably heard about it in the standard model and the Yukawa coupling, but what makes it so important? And then, of course, the PDF. If you want the PDF, please comment because there's a lot that was just used to simplify or a lot of extra steps in the simplification of these two questions that are left in the PDF that you might want. But feel free to comment and I'll send the link to you and then you can download it from there. You'll be good to go. If you're curious about the world of science, be sure to subscribe. I post educational content every week to quench your thirst for curiosity. So with this, let's jump straight to stop number 1, problem 10. Alright, so in this problem, it's not too bad of a question. We just need to assemble all the parts in order to assemble a solution. And to start, we are given that the potential of a soft sphere is given by equation 10.81, and this differs slightly from what we saw with the hard sphere where this was infinity, or maybe you remember the delta potential, instead of V naught, some arbitrary potential, okay? So soft sphere, hard sphere, that's kind of the intermingling relationships, okay? Now, we need this potential in order to use equation 10.88, which gives us the scattering amplitude, okay? Now, note that this integral goes from all space, so 0 to infinity for all of r, okay? But note that our potential here is piecewise. So we want to split it up from 0 to a as color-coded, then a to infinity as color-coded, and then plug in each part respectively. Now, because the potential is 0 for a to infinity, this whole integral goes away and we don't care about it. We don't have to deal with it. Cool. Thankfully, this V naught is just a potential, or a constant rather, so we can bring it outside as we see here, and that leaves us with the product of r and sine. Since this is a product, we need to evaluate this integral, implementing integration by parts and hence the color code. Let's get to how we do that. So in integration by parts, we need to define u and dv, and then find du and v, and here's how we do that respectively. Now from there, integration by parts tells us that we need uv minus integral v to u. Okay, I've been tutoring a lot of Calc 2 lately, and I'm noticing here that people tend to forget to evaluate the boundary term at the limits. So don't forget that when you're doing this integral and any type of integration by parts there on out. Okay, so we notice here that this negative 1 over kappa is just a constant, bring it outside, that does not get evaluated within this regime. This negative and negative cancel, leaving us with a positive. Again, bringing 1 over kappa out. Now we can evaluate this boundary term and execute the antiderivative on this cosine, leaving us with the 1 kappa sine evaluated at the boundaries, or the limits rather. Here, the boundary term, we have upper limit minus lower limit. That 0 makes our life easy and gets rid of that second term. Now we need to evaluate the sine, and then we see here that we have sine kappa A minus sine kappa 0, but then that whole argument goes to 0, and then that sine term, sine of 0 goes to 0, so we get rid of that thing, which is awesome. Simplifies us much quicker than we thought. So we have all our constants out front. We have a simplified or evaluated integral. Now we need to simplify this expression. Okay, we notice that we have a kappa squared here. So we're going to multiply by 1, but we'll change the 1 to actually fit our algebra. And the 1 in question here is just a kappa over kappa. That allows us to pull out a kappa squared from both of these terms, and that's what we see here. Okay, this leaves a leftover green kappa on the cosine term. That's not too bad to deal with. So after we do that and we simplify, we get a kappa cubed here. Change the order of these to cover that negative sign. We don't like leading with negatives. Okay, so we see that the scattering amplitude is given as this. That's not too bad. Okay, but here kappa is defined by equation 10.89, which is given as 2k, the wave number, sine theta over 2. So again, small angles here, we're dealing with that again. And here, as a result, in the low angle energy, the approximation scheme that we have for low energy, we're told that the kappa A is much less than 1. And what this translates to is the small angle approximation for both the sine and the cosine. Okay, so if we expand these out in a Taylor series, that small angle shows that we truncate any of the higher order terms after about the first 1 or 2. Okay, so that's what we see here. After that, if we want to apply these to the scattering amplitude equation, we do so up here, color code. Now all we have to do is distribute this kappa A in the green terms, and then we see that we get a kappa A cancel. We have a kappa A cubed, beautiful. That tells us that we have kappa cubed, A cubed in both numerators, and color code that purple so we can factor it out. Again, we're left with a something over 6, something over 2, so we're going to have to multiply by 1 to make a common denominator. That 1 turns out to be 3 over 3, not too bad. After we factor out the kappa cubed, A cubed, we can cancel the kappa terms. Beautiful, makes our life easy. And then we're just stuck here with, negative 1 6 plus 3 6. Clearly that simplifies to 2 6, reduces to 1/3, and then we see we get this expression. Now, this expression, putting it into, some numerical constant or numerics up front, all the constant terms here, we see that this is actually equal to what they got in the book with reference to, well, we had the same potential, and now we're just finding the volume of a sphere or the integral of the spherical coordinates. Okay, so this 2 pi and this 4 pi reduced to a 2, which is what we see here, and then all the other constants are the same and matching, so we get an identical result. And thus we conclude problem 10, not too bad at all. Okay, so if you're finding this helpful, don't forget to give it a thumbs up. It helps more curious minds like you discover this content. Now that we're done with problem 10, let's jump straight to 11. All right, and this is stop number 2. Again, this is pulling from example 10.5 in a book dealing with the Yukawa potential and finding the scattering amplitudes. Okay, and in the integral for finding the scattering amplitudes, the Yukawa potential left us with a exponential and a sine. Okay, and trying to do integration by parts on that is just going to lead to a self-referential integral. because neither the exponential nor the sign disintegrate or vanish with more derivatives. We just keep getting a cyclic group. So instead of using integration by parts over and over again until we establish a pattern, why not just use tricks from complex analysis and not integrate by parts at all? Okay, and this trick is based on Euler's equation, and this will be the star of the show, all things considered. So if we know that e to the positive argument, so long as it's complex, leaves us with cosine plus I sine, then the negative leaves us with the negative I sine. So then subtracting these two equations, we have the blue minus the green, and when we apply the minus sign to both the green terms here, we note that the cosine terms cancel, leaving us with the reduced form of 2i sine with the arguments. Okay, so we could solve for sine by just dividing by 2i. This is much simpler than trying to repeat integration by parts. And the integral in question here comes from equation 10.91. Okay, so this exponential and the sine, none of those go away with integration by parts. So we're just going to keep piling up over and over and over again. Okay, so instead, let's go ahead and substitute the sign in terms of the exponentials, which is, a great trick to have in mind. You could also do the same thing for cosine. This makes our life easy. Okay, so from there, then we see here that we have e, we can bring this 1 over 2i out front. It's a constant, no big deal. Now we need to distribute this exponential into the bracket. We do so here, but we also notice that we're on the same base, so we can add the exponents. So that's what we do here. Note here that we also have a common factor with something on an r term. So let's factor out the negative and the r. Left side factor for the negative, right side for the r. We have a negative on this mu and a positive, which we have to turn to a negative. That's what we see here. Then both of these have a negative, so that turns that to a positive. We're good to go. Now from here, all we have to do is split up this integral, and we could solve this with relative ease, all things considered. Okay, so once we split up this integral, now we're just in a situation where a simple u sub will be sufficient to handle these two integrals. And the application of the u sub, just to keep everything in order, is given in the PDF, and we see the work here. If we let u from the blue equal all this, du, solve for dr, now we have that. Go ahead, change the limits. And again, since we're in a low angle approximation thing, we're assuming that this k is small, so that mu is bigger, and we don't have a sign change due to this argument. So that leads to negative infinity, 0, leaves us with 0. Rinse and repeat for the green. And now we see where we get our new limits and all this stuff from the u sub in to the integrals. We see here that the negative from the integrals and this negative from the substitution cancel. Beautiful, get rid of it. All nice things. All of this stuff in the denominator is a constant. Constant, bring it out front. Now we see that we just need the integral of e to the u or e to the v. Very easy to do. Boom, there we go. Now we have our limits, evaluate it. This e to the negative infinity goes to 0, although it's an improper integral. We just kind of hand wave it in physics, so we're all right. Then e to the 0 goes to 1, so we end up with 0 minus 1, 0 minus 1, and that leaves us with a negative 1 in the brackets, so let's clean this up. All right, negative 1, we see the negative cancels. Now this negative goes here, that's what we see there. But again, we see that we have two different denominators, so we need to find a common denominator. In this case, finding the common denominator is also multiplying by the conjugate pairs. So this is beautiful. It's going to simplify great. Once we find a common denominator here, we can push the fractions together. We said this negative sign goes here, so we can distribute that into the blue parentheses while also foiling out this denominator. Mu and mu give us mu squared. Then we have this negative I kappa mu right here, mu and I kappa here, and then negative I kappa, and then positive I kappa leaves us with negative I squared kappa squared. But after we distribute and simplify, mu and mu cancel, beautiful. The cross terms here cancel, beautiful. And then we simplify up here, I have I kappa, so it leaves us with 2I kappa. And that 2I cancels with the 2I out front, beautiful. And then we see that we have I squared, that turns to negative 1. Negative, negative cancel, more beautiful. And then all that we're left to do is, now that we evaluated this integral, is to plug it into the scattering amplitude equation. And we see that, well, here's our total equation for the and then we have the integral here. Now we have kappa kappa that are going to cancel, and we get the result that is found in example 10.5, and thus this concludes problem 11. Again, not too bad, but now that we can kind of see more tricks, the more we see these tricks, the more reps we get, the better off we're going to feel in whatever else we see in the future. So really, really cool to see. All right. Well, again, thank you all for watching. This has been a fun video to make and really quick, all things considered. Um, and as a result, we see a lot of different tricks coming up again, and we love that. So if you don't mind, please share this with a friend who's also curious about science, and let's grow this learning community together. We're definitely going to need it in the next wave of, all the content coming out, especially with AI and new learning platforms and techniques. The more we can learn together, the better off we'll all be. So please help in that mission of growing this community. In summary, again, you saw how we kind of dealt with these scattering amplitudes, and more importantly, you get an overview of the whole concept of why these approximation schemes are used. Wave equation, integral form with the Green's functions, then to the, approximation schemes, Born series, Born approximation. Whew, this is a lot. Born approximation makes its money because of scattering amplitudes. That's where we're cool at. So, thank you again for everybody who supported the mission up to this point, especially all the new patrons that have joined us. Can't wait to hear and continue getting your feedback. That's been amazing to see, especially for some of the reviews. That's been very helpful. Makes me want to keep going for sure. So thank you, thank you, thank you. Books, notes, and other reference materials are found below, especially that cover image. That's a really cool page, and I think they even have a group chat that you could join, or Discord, something like that. So be on the lookout for that reference. I'll definitely post that below because that's really cool. If you have any questions, please feel free to reach out. As always, thank you for watching, and until next time, stay curious.